Antarctica is one of the most captivating environments on Earth. It's the highest, the driest, and the windiest continent. It really is a place of extremes. It's also the most remote, which makes it easy for us to forget sometimes that what happens at the poles affects us all. The Antarctic ice sheet contains enough ice to raise global sea levels by 58 metres if it were all to melt. Now that would be enough to inundate many of the world's major cities, including London, Shanghai and New York. Scientifically too, Antarctica is fascinating. However, its remoteness makes it difficult to collect data there, so we unfortunately have fewer observations of different parts of the Antarctic environment, like the atmosphere, oceans, glaciers and biology, than we do elsewhere on the globe. Using MASIN is one way that the British Antarctic Survey, or BAS for short, is trying to minimise that data deficit. But firstly, what is MASIN? MASIN is the British Antarctic Survey's atmospheric science research kit that gets installed on board one of our Twin Otter aircraft to collect scientific data. BAS has 4 Twin Otters. But only one is configured to carry the MASIN kit. When fitted, the aircraft can measure a huge array of properties, such as cloud physics, atmospheric chemistry, and interesting weather phenomena. These things can inform us about the properties of the Antarctic atmosphere and help us answer important scientific questions about meteorology and climate in the Antarctic. Aircraft are especially valuable tools for atmospheric research because we can fly directly in or through whatever we want to measure. Ground or space-based measurements typically rely on indirect methods to calculate what you're interested in, whereas in an aircraft, you can sample the air directly. The aircraft can be altered to measure pretty much whatever you want, but she always measures core variables like GPS position, temperature, pressure, humidity and radiation. Here's Tom and Russ to explain.
We're going to put a pair of radiometers on here, measure the upwelling radiation in comparison to the ones that Tom's just put on the roof.
We are just about to go and start putting the pylons on the aircraft. We can put 2 pylons on, but for this campaign we're only going to have 1, and we're going to have a cloud probe on the pylon that measures the particle size and whether it's an ice particle or a water droplet.
Once we've got the aircraft fitted, then the real fun starts and we can go out flying. But first, we've got to make sure that we know what our science aims are. Before we fly anywhere, we always do a flight plan, and this is one of them. We're going to do an L shape over water and then over some sea ice. Most of the flux data we have to collect at low level, so we need to fly at around 100 foot, which is very exciting.
So overall mission then is flux measurement over the Bellinghausen Sea. Weather, we've talked about a lot here, is very nice apart from this crosswind, which is beginning to dissipate now. I just need to do a final check of that. And then on task in the Bellinghausen, it should just be medium to high cloud and about 15 knots on the surface, so it should be really good conditions for what we want to do.
Here's Alex to describe what we're going to do.
So we want to go hop over the market bay where it's very windy and go down here to the sea ice area and then fly a low level leg over that in the direction to the open water.
During the flight, one scientist usually looks after the instruments, while another is up front with a pilot, making decisions about whether the flight plan needs to be adjusted to get the best scientific data. We write a log of all the events during the flight so that later we can cross-reference any interesting features in the data with what was going on at the time. During the 2017-18 summer field season, we were flying as part of a project called ORCHESTRA, which is trying to understand the role of the Southern Ocean that surrounds Antarctica in moderating climate change. So to do this, we were measuring the flow of heat and gases like carbon dioxide in and out of the surface of the ocean and of sea ice. The data we collected will be used to improve estimates of how much heat and carbon the Southern Ocean absorbs and how this is likely to affect future climate change. To find out more about MASIN and the atmospheric science we do at BAS, head to www.bas.ac.uk and search for Airborne Science and Meteorology.